For my technical topic, I will be delving into the realm of field programmable gate arrays, otherwise known as FPGAs, specifically focusing on the redundancy and partial reconfiguration bitstreams. My intrigue with this topic was kindled during my capstone project, where our team was tasked with constructing a secure boot controller capable of loading in partial bitstreams. As I delved deeper into ensuring the integrity of these bitstreams, the realms of redundancy and error detection came to the forefront. Their complexities and significance not only captivated my interest, but also underscored their relevance to the broader theme of FPGA security. FPGAs represent a unique category within integrated circuits. Unlike traditional chips that have a fixed function throughout their lifespan, FPGAs are designed with the capability to be reconfigured after they've been manufactured. This versatility allows them to be tailored to a wide range of industrial applications. However, the dynamic reconfigurability of FPGAs also introduces inherent challenges. The ability to modify the device's configurations on the fly requires rigorous security measures. Ensuring that these configurations remain genuine and free from tampering is paramount. Malicious alterations could jeopardize the system's entire functionality and the integrity of its data. Thus, while FPGA's adaptability brings immense advantages, the need for secure, reliable, and authenticated configurations becomes critically important. Partial reconfiguration is a fundamental aspect of FPGAs, grounded in the concept of selective adaptability. In this approach, specific reconfigurable regions of the FPGA can undergo changes, while the non-configurable sections operate without interruption. This dual functionality ensures that as a segment of the FPGA is modified or redefined, the overall operation of the chip remains consistent and uninterrupted, guaranteeing the smooth functioning of the system. As an example, we can consider a satellite that both monitors Earth's climate and communicates this data to ground stations. When requirements change for a communication protocol on the satellite, we can apply the requirement via partial reconfiguration. The satellite will be able to continue its climate monitoring while the FPGA updates the communication module, thus showcasing the adaptability and uninterrupted operation enabled by partial reconfiguration. In FPGA configurations, the dual challenges of reliability and security take the forefront of one of the most critical issues to solve, as often these devices serve critical roles in sectors such as aerospace, medical devices, and defense. Addressing the challenge of reliability, one approach we can take is redundantly checking our partial bit streams using the concept of triple modular redundancy. Triple modular redundancy employs a majority voting mechanism across three individual copies of a bit stream, where each configuration is treated as an independent logic unit. Each of these configurations are checked across three separate redundant logic units, and by comparing the outputs, the majority vote is taken to determine the correct bitstream output. This approach offers a twofold advantage. Firstly, malicious actors face a significant hurdle. They will need to alter at least two of the three bitstreams to compromise the system. And secondly, environmental factors such as radiation can cause unintended disturbances in configurations known as single event upsets. However, with TMR, even if one bitstream is affected, the other two ensure the system remains operational and unaffected. This dual shield of security and reliability makes TMR an invaluable tool in FPGA configuration. FPGAs with their dynamic reconfigurability stand at the forefront of adaptive hardware solutions. Their ability to evolve post-production makes them versatile tools in various industries. Yet with this adaptability comes challenges, especially in the realm of security. The very bitstreams that offer flexibility can be vulnerable to tampering and environmental disturbances. However, as we've explored, techniques like triple modular redundancy provide a robust solution. By triplicating configurations and using majority voting, we can ensure the reliability and security of FPGA operations, even in the face of potential threats. Innovation in research, such as the work by Katzenschmidt and colleagues to find optimal approaches to redundancy checking, we continue to push the boundaries, optimizing these techniques for real-world applications. In conclusion, FPGAs encapsulate the spirit of modern electronics, dynamic, adaptable, but not without challenges. As I conclude this discussion, I'd like to emphasize the value of the references I used while creating this presentation. For those keen on exploring further, these sources are great starting points for further understanding FPGAs and their reconfigurable nature. I wholeheartedly recommend delving into them to enrich your understanding and perspective on the topic.